Hello, and welcome to a video on query planning and optimization. So when a SQL query comes into a database, we want to do two things. Well, really one thing. We want to come up with a plan, an actual step-by-step set of operators that are going to execute that query. And then the second part is we want to come up with an optimal, or at least a very good, efficient plan, as opposed to, as we've seen, there are choices that a database could make that would result in very long-running or inefficient queries where better options exist. And so this area of query optimization goes all the way back to one of the first relational databases created by IBM in the 1970s, System R. And up until that point, people thought that it wouldn't be possible for a database system or any software to come up with better query plans than a human could. This was similar to when the C compiler was first created. People said, look, we have experts that know how to handwrite assembly code. There's no way that a compiler, some mindless program, is going to generate better assembly than the experts. And in fact, today, compilers generate almost all the assembly that runs on computer systems and do an excellent job, and in almost all cases are doing as good or better than a human could do. And in System R, the IBM folks did this for query optimization. In particular, an applied math PhD from Harvard, Patricia Sellinger, a researcher at IBM at the time and for decades afterward, came up with System R. They just sort of divided the different pieces of the database system among different researchers who were working on this project. And Patricia worked on the query optimizer and published the first the first paper about how query optimization is done. And the reason I bring this up is that many of the ideas from IBM System R, many of the design choices and concepts that they came up with are still in use for query optimization today. So I want to kind of lay out the big picture of kind of how the query optimization and planning process is going to work. So we have some application. This might be a web page, a mobile phone app, whatever it is. This is what is generating our SQL query. So out of this application, we get our SQL query. And the first thing that this might encounter is, so let me put this in a different color. I'll put the parts of this diagram that are optional, that could be part of a planning and optimizer, but are not kind of a required piece. I'll put these in red. So this optional part is what's called a Sql Rewriter, which would take an incoming SQL query and perhaps rewrite it in an equivalent but more efficient form. And so this is not that common, but there are some databases that do this, that will kind of, as a pre-processing step, rewrite parts of SQL queries. From this, we would move on to the parser, the part of the database that's going to just kind of understand the different components of a query. There's the select clause and the from clause and the where clause, and this is handling the syntax and produces what's called an abstract syntax tree. And parsing and abstract syntax trees will be a familiar concept if you've taken CS 251, but we're just turning SQL into a kind of abstract representation that we can work with for the other parts of the system. So next, we would move on to something called a binder, which is going to take the sort of string names that were in our query and replace them with some sort of internal IDs. And to do this, it's going to get information from the system catalog. Information about what are all the tables, what are their attributes, what are the indexes, etc. In our system. This information is kept in the system catalog. And so in the binder, we're going to take all the names, which may be kind of lengthy strings. We have to think about case, what case they in, etc. And so in the rest of the system, we don't want to be referring to the tables and attributes and so on by some string names. We just want some internal ID that we can use to look up the information we need. So the binder is going to use the information from the system catalog to turn names into these internal IDs. And then the output of this binder is going to be a logical plan. So we've parsed our SQL into kind of the different into a tree structure with the different clauses, and we've filled in the names with these internal IDs. So now we have a plan that logically describes, all right, we're going to join these two tables, or we're going to use this table as an input. What the logical plan does not have at this point is the specific algorithms and those sorts of details that we would actually need to execute a plan. And that's coming later as the physical plan. So our logical plan is sort of high level, like what are the steps involved. The physical plan is like is like, all right, use sort, merge, join in order to avoid a later order by operator. That's the sort of thing that would come in at the physical plan. So from this logical plan, we have another rewriter, this time a tree rewriter. And this is more common than the Sql rewriter, that our planning will have a step where it might change this tree, this logical plan around in order to improve it or optimize it. And we'll see examples of kind of rewrites that a tree might do. And this is going to be based on just set rules or heuristics. That is, we're not doing any sort of estimating of how long something will take or comparing different possible plans at this point. We have some rules that when we see a tree that matches some certain pattern, we make a particular transformation on it. And again, we'll see examples of this. After we've done any tree rewriting, which will also need information on the database schema, on kind of the attributes and things like that from the system catalog. Our tree rewriter will send the logical plan to the optimizer, and this optimizer is going to rely on a cost model, and this is the part where we are actually estimating things about how long different possible plans might take. That's what this optimizer is doing, and it has some cost model that says that is setting up how these estimations take place, and we'll get into more details later in the video about kind of what stuff goes into this cost model. But out of the optimizer would come the physical plan, the actual, here is the operator, the function that should be called to do each step of our query. So that's this kind of big picture of how planning and optimization is going to take place. And there's not always going to be a sort of one-to-one mapping between this logical plan and this physical plan. There might be sort of different transformations going on. And the thing to take away from this diagram is that there are kind of two types of optimization strategies that we're going to go into more detail about. One is this rules and heuristics. What sort of transformations would we do on this logical plan to make it more efficient? And second is this optimizer that is doing some sort of estimation of the cost of different possible plans in order to produce a particular physical plan. So we're going to start with these rules and heuristics and then move on to the cost model. So I guess one thing to say about optimization overall, as well as at this point, is that it's extremely challenging to do well in practice, that major database companies spend millions and millions and millions of dollars trying to make their query optimization better, to beat the competition. And for this reason, the kind of expensive commercial database systems like Microsoft SQL Server, Oracle, DB2 from IBM, these are the ones that tend to have the best and most sophisticated query optimizers as compared to the free open source like Postgres or MySQL. People have looked at using AI, bringing AI into this process, the optimization piece in particular. These efforts have been fairly unsuccessful so far, but that is something that people are currently trying to develop further. All right, so tree rewriting. So there are kind of a set of these rules that you might apply, and I want to show how that would work with a specific example. So let's say I had a database about Roman emperors, like you do. So I might write a query where I want to find the names of the emperors who died of natural causes. And let me tell you, that was quite an accomplishment for a Roman emperor. Very few of them made it to dying of natural causes. A lot of assassinations, it turns out. All right, so I might say I want to select the name from my emperor and death tables where we'll join up the tables where emperor.death equals death.id, and type of death is the string natural causes. All right, so if I translate this query directly, kind of just as written, directly into a logical plan, I might have something like emperor and death go into a cross product, right? I'm just selecting from both of them, that's what that says, which goes into a selection, which has all of my where clause, this, and from here we go into a projection of the name column. And so there are kind of a set of rules that I might consider applying here. So we're going to split conjunctive predicates, and conjunctive just means our ands. And so we're going to split that up. Another thing we might do is called predicate pushdown. We'll want to replace our Cartesian products with joins where possible, and also do what's called projection pushdown. So we'll start with our splitting up of our conjunctive predicates. That means we have this one selection that's a conjunction of both of our predicates here. We can actually split that up into two different selects with each of our conditions. So when we split it up, we now have two of these selection operators with each of our things. We still have our cross product of emperors and deaths. And so we've split our conjunctive predicates. We now do predicate pushdown, which means we want to do these select operators, this filtering, as early as possible in our query plan, so that we have kind of fewer tuples that we have to carry forward up into the later operators. And so we won't be able to, the selection that compares the fields from these two tables, we can't move it below the cross product because it needs tuples from both of our relations. But this other selection is just on one of our relations. So we can actually push that down and filter out some of the entries in this relation before we get to the cross product. Now we'll reduce the total number of tuples that would go up further in our plan. So we rewrite it like this. We go to our selection on type, and from there into our cross product into our other selection. And from there into our projection. So we've pushed down our predicates, and now we want to replace our Cartesian products with joins. And so we know that writing a query like this will join these two relations on using this predicate. And so we're just going to combine we don't want to generate the full Cartesian product and only then do the selection. We actually just want to do a join. That's going to be a lot better for us. So we replace these with our join. And that would go into our projection. And finally, our projection pushdown says, all right, in a row store database, in any case, we're taking the whole tuples of these relations and feeding them up. But we know at the end we actually only need the name. And so if this emperor table has a ton of columns, all sorts of different stuff about the emperors, we don't really want to pay the memory overhead of materializing all of those attributes all the way up our plan. So this projection pushdown says, like we push down our predicates, we're going to try and do the projections as kind of low in our query plan as possible. So what we can do is the things we need out of an emperor are the death and the name. So we have a projection immediately that gives us just the two fields that we need. And then for our other relation, we need the type and the ID, and that's it. We could put the projection before or after the selection. I'll go ahead and put it after. So once we select from the type, the only thing we need from this relation is the ID in order to do this join. And because our projection at the end doesn't need any of that, so we'll just project up the ID. From these projections, we go into our join, and from there into our final projection of just the name. And so we just had these rules, these heuristics, which said, all right, if we see a query plan that matches this sort of pattern, meaning that we have this conjunctive predicate, we're going to split it up. All right, if we have predicates, we're going to move them down in the tree as far as we can. If we have a Cartesian product and a predicate, turn that into a join. If we have a projection, again, push that down. And at no point in any of this did we need to actually look at the data in the tables. We needed information about the schema, about what columns we have, things like that, which we'd get from the system catalog. But we didn't actually need to look at the data itself. We're not doing any sort of estimate of how many tuples specifically would be involved in one of these plans versus another. We're just applying these rules. So this is not an exhaustive set of all the kind of tree rewrite rules that we could apply, but it illustrates the kind of things that our planner and optimizer are going to be doing. So another thing that we might try and optimize is identify when queries involve predicates that we don't need or that we can combine in some way. So let me give you some examples. So we might have something like select star from emperor where ID equals ID. And you may say, well, ID is always going to equal ID. So why would anyone ever write a predicate like this? Like, this doesn't seem to make any sense. And I agree. Seems a little silly that someone would write this exact SQL query. But one thing that is important to keep in mind when we're thinking about databases is that the queries are going to be generated not, in fact, much of the time, not by hand written SQL, but by dashboards or applications, libraries. Like someone goes to a web page and there's an interface to enter some search criteria, and that generates on the back end a SQL query that's sent to a database. And so if we're thinking about all these different interfaces, different situations where we might be getting queries from, it's easy to imagine that within some of those, it's possible and maybe even common to generate queries that have sort of unnecessary appendages like this where clause. And we'd like our query optimizer and planner to be able to recognize, look, this isn't necessary. It's no use doing the extra work of applying this predicate to every tuple from our emperor table. And so this would be one where the tuple could be identified as unnecessary, and then the actual query that the database would execute would just omit that predicate entirely. And this is something that again, higher end systems can do. DB2, Oracle can do this. Unfortunately, Postgres cannot do this. That if you write a query like this in Postgres and you look at the query plan, it does not get rid of it. It's going to execute this check on all the tuples that it's retrieving, even though it doesn't need it. Another example, if you write ID does not equal ID, well, that's always false. And you could really save yourself a lot of time by saying, oh, well, this predicate's always false. I don't even need to scan the table, just return an empty result. Again, some systems can do this, Postgres cannot. Another interesting, in the same vein, kind of optimization would be merging predicates. So if we had our select, we're again selecting from our emperor table, and we're saying where some begin year is between 50 and 150 AD, and begin year between 100 and 200. Us as humans looking at this can see, well, 50 to 150, 100 to 200, it's actually only going to be 100 to 150 is the actual range that this represents, and so we could rewrite it to be just a single where begin year between 100 and 150, and that would result in instead of checking the date, checking this begin year twice, we're only checking it once. And sadly, Postgres can again not do this, but some other systems can just identify, oh look, these two between or also two in predicates can be simplified and merged together. All right, so that's the sort of operations that we would do on our logical plan before we bring in the cost model. So let's transition to talking about these actual cost estimates. And so our task here is to go from a logical plan to a physical plan. So this says, all right, we have a join in our logical plan. What join algorithm should we use? All right, we have two tables that we're accessing in order to join them together. Which access method should we use? Should we do a sequential scan? Is there an index we could scan? And these are all the types of decisions that the system needs to make to go from our logical plan to a physical plan, and this is where this optimizer comes in. And there are sort of three categories of costs that our optimizer might account for. So we have physical costs, and these are the different kind of physical attributes. How much CPU is it going to use? Kind of just how many CPU cycles, how intensive will this plan be? The one that we've been overwhelmingly focused on, and which will be the case for disk-based database systems, is disk I/O. How many reads and writes are we doing from disk? That's likely to be a bottleneck. We've also seen cases where we have to take into account the amount of memory used. For example, when we're deciding between something like quicksort versus external merge sort, that's going to be deciding, all right, how much memory do we have available? How much will this plan, this potential plan use? If we have a database that's like distributed in different places, different computers, maybe far apart from each other, we might need to take network into account. Does this query plan involve a lot of retrieving data from somewhere far away? And so all of these costs are going to rely heavily on the specific hardware that a system is running on. Kind of how slow are disk IOs depends on the disk you're using. What memory use? How much memory do you have available? And so this is going to often need to be customized to a specific hardware. Other kinds of costs we have. Logical costs, which are kind of in terms of estimating the kind of number of tuples that this plan will involve moving around. So we might need to estimate, all right, for this particular plan, how many tuples do we think will need to be transferred between these two operators, because that's not a costless operation. And if we can say choose make a different choice and shrink that size, then our logical costs will go down. And the last is our algorithmic costs, which are going to be the complexity of the algorithms that we choose for our plan. So we've looked at nested loop join versus sort merge join versus hash join. All of those had some complexity in terms of the number of pages or tuples of the relations involved, and so that's going to be the third component of our cost estimate. Important to note that the cost that this cost model, this estimate is producing, is going to be a unitless quantity that is only relevant for comparing two potential plans. That our cost estimates are not going to be in terms of a specific number of seconds that we expect the query to take or something like that. It's going to be just some number that we assign to the query based on these different properties that we're using to compare to other queries. Speaking of kind of where these numbers come from, different systems do it different ways. Postgres, for example, has a bunch of sort of magic constants that it uses. For example, it says that processing a tuple in memory is 400 times faster than reading it from disk. And it also notes that, unfortunately, there is no well-defined method for determining the ideal values for these variables. They're best treated as averages over a mix of queries, and changing them based on only a few experiments is very risky. So they just sort of came up with some numbers that seemed to work well, and maybe you want to change them for your particular instance of Postgres, but this is what determines its estimate of what things cost. We can see that it says, all right, sequential page cost, like reading disk pages sequentially, is 1. Reading disk pages randomly is 4. So it says, all right, random I/O about 4 times slower than sequential I/O, but that might not be true for a particular instance, but this is kind of the approach that Postgres takes. IBM's DB2, in contrast, will incorporate kind of a bunch of micro benchmarks about the particular environment it's in and other instance-specific info into its cost model. This is why you pay IBM the big bucks when you purchase kind of a license or installation of DB2, is that they're doing a lot of stuff for you. All right, so these are the things that are going into it. What sort of things are we actually computing? One key aspect is going to be for predicates. How selective are they? That if we want to estimate how many tuples are going to be involved in in some part of our query, that will probably depend on how many tuples get filtered out by a particular criteria. And so we're going to want to estimate the predicate selectivity. So what fraction of the tuples will this predicate be true for? So how will it affect the data further up our query plan? And so kind of in a simple approach, these estimates might make some pretty strong assumptions, like that the data is uniformly distributed across the different possible values, that all predicates are independent from one another. And so it might say something like, all right, we have a select star from people where age equals 20. So the cost model might know that age goes in this database from 18 to 99. And so it says, all right, well, 20 is one out of these 82 values, and so we expect this predicate to give us 1/82nd of the data. So it might estimate that the selectivity is 1/82. But the actual data may be quite different. Maybe age 20 is much more common or much less common than other ages. And so these estimates are sort of approximations only, and we wouldn't want to, for example, in order to estimate how a particular plan for this query, how much it will cost, we wouldn't want to need to run this query or other queries in order, as part of the planning phase, in order to get a better estimate. Like we need every time that we have entered a query in Postgres or SQLite, in fractions of a second, it has done this whole process of coming up with a plan, comparing the cost of different plans, selecting the best one, and actually running it. And so this all needs to happen very, very fast. We can't sort of dwell on getting it exactly right. We just need our kind of best estimate. Now, this sort of assumption of uniformity can get us. This assumption of uniformity can get us into trouble. It's also the case that if we assume that two predicates are unrelated, we can, even if our uniformity is a correct assumption, if we don't take into account that predicates can be correlated, we can get into trouble. So, for example, if we had a perfume database, as in a database of different types of perfume, we have 10 brands and 100 fragrances. And we had some predicate where we wanted to say the brand is philosophy, and the fragrance is Amazing Grace, well, one approach might be to say, all right, well, we're doing 1 out of 10 brands and 1 out of 100 fragrances. And so our selectivity is going to be 1 out of 1,000. But in fact, Amazing Grace, the fragrance, is made by philosophy. So if we're selecting Amazing Grace, then that implies philosophy, and also saying brand equals philosophy doesn't make this predicate any more selective. So the real selectivity is just 1 out of 100. So we're off by a factor of 10 in terms of estimating how this predicate is going to affect the number of tuples that our plan is working with. And this is why high-end systems will actually compute statistics about correlated columns. We'll actually compute this sort of information that that this brand and fragrance columns are related and are correlated and be able to take that into account. So in addition to these sort of correlation stats, in addition to these sort of correlation stats, our databases will also kind of maintain histogram-like information. So as part of doing these sort of selectivity or other sorts of estimates, our database might maintain information about the fact that some particular attribute has a distribution that looks like this, that there are some number of tuples that have a value of 6, not very many that have 4 and 5, a lot that have 3, and so on. And kind of maintaining this sort of frequency information can help make our estimates more accurate. And you may be wondering, are there actually like charts stored within the database? Not quite. This sort of histogram information would likely be stored in a hash table. And so the actual representation within the database system would be something like something like this, where we have the value and count in information stored in some sort of hash table. And if our data has a lot of unique values for attributes, we might not want to store the count for every single unique value. That might take too much space. For example, here we're just storing six integers, 24 bytes. That's basically nothing. But let's say we had a billion different values that an attribute had in our or could have in our data. Then that's a billion integers. That's 4 gigabytes just to store the histogram. So we would not want to store the count for literally every distinct value in that case. And for that, we might do things like store it for ranges of data. Where we say, all right, 1 through 3, there are 19, and 4 through 6, there are 8. And so now within each of these bins, we might make a uniform, assume the data is uniformly distributed, which would introduce some errors. But we'd save a lot of space, so maybe the trade-off is worth it. Instead of these equal size bins, we could have we could choose kind of these ranges such that the amount of data that falls into each range is about equivalent. That is like making these quantiles rather than fixed width. But in either case, histograms are going to be useful for doing these sort of cost models. Another thing that can be a useful strategy that I just like to mention is sampling. So if we have a table of a billion tuples, maybe we could instead maintain a sample, 100 or 1,000 tuples, and we compute statistics about that sample, or scan the sample in order to compute the statistics we need, and that would be a way of getting a decent estimate for what the billion tuples may be like. One other aspect of all this sort of statistical data that I'm talking about is that if we have a database that has a lot of updates, inserts, deletes, modifications, we don't want to make all those operations a lot more expensive by adding on the cost of updating all the histograms or the samples or whatever it is every time we do the update. So for these sort of statistics, there are different ways that we might kind of cause them to be computed. They might be computed manually. A lot of databases have some command that you can run to tell it, all right, update all your statistical information. They might be scheduled. So you have a heavily used OLTP database during the day, lots of inserts and updates, and then overnight, when there's very little activity, you have all these tasks scheduled to kind of update all the statistics about it so that they're ready for the next day's workload. If it's the case that that doing these updates would not slow down the queries too much, or the performance is not critical for the inserts or updates, you could recompute these statistics along with every query, or have them run whenever the database is updated. All right, the last thing that I'd like to talk about is how does the query planner optimizer decide which plans it should consider? And this is the issue of plan enumeration. How are we generating possible plans to look at? Which plans will those be? Because the point of the query optimizer is we have a logical plan. We've done our tree rewrites on it and so forth. And now we want to consider different physical plans that correspond with that logical plan and estimate the cost of each of them and choose the one that has the lowest cost. So for single relation queries, meaning we have a query that just involves a single table, there's no joins, just data from a single table. This we can actually, and in fact, kind of newer database systems will do this simply with heuristics, with rules, rather than doing a full plan enumeration, cost estimate, and so forth. And the key thing that we often need to decide for these single relation queries is what access method should we use? Is sequential scan? Are there indexes we should use? Which index should be used? And these single relation queries are kind of can be simpler to choose a physical plan for because there often exists a best index that the database system could choose in order to provide the query. So the kind of real interesting part of this is for our multi-relation queries, and these are queries that do involve joins, perhaps many joins. And one decision from System R, IBM's original relational database that has kind of carried through to modern day is that we're only going to consider when we're thinking about different possible plans, left deep join trees. And so what this means is, let's say we want to join A, B, C, and D, 4 relations. So we might have a plan that looks like this. We could construct one like this. Construct something that looks nice and balanced like this, but this consider only left deep join tree says we're just considering trees like this. We're just considering ones where we join 2 and that feeds into another join with another one of the tables and a kind of pipeline like this. And so we're just not going to consider join trees like either of these. And so this will greatly shrink the number of possible plans that the database is going to consider and make this whole optimization process more tractable, more feasible to actually compute if we limit ourselves to just these left deep join plans. And in order to kind of generate possible different plans, our optimizer is going to enumerate relation orderings. So this means if we're, say, joining R, S, and T, 3 relations like this, we might join R and S and then T. We could instead join R and T and then S. We could join S and R and then T. We could join S and T and then R, and so on and so forth. So we're enumerating all these different kind of relation orderings in terms of where they occur in our joins. We then, for each one of these, we're going to enumerate the choices for our join algorithm. So let's say that we're doing it for each of these different relation orderings. We're then doing the algorithm choices. But let's say that for example, take this one, and then within this structure, we might say, all right, we could do a nested loop join and a nested loop join. We could do a hash join and a nested loop join. We could do a nested loop join and a hash join. We could do both hash joins. And so on and so forth. So for each of these relation orderings, we're then going to generate a plan with different join algorithm choices. And then for each of those, we're going to enumerate the access method choices. So maybe I take, for example, this one here. We're going to do it for all of them, but for example, I take this one, and now for, we might use a sequential scan. On T, and sequential scan on our relations R and S as well. Alternatively, maybe there's an index that we could use on S. So another plan we consider is index on S and still sequential scans for R and T. And so what we get is this huge number of possible plans where we've enumerated different relation orderings, different join algorithm choices, different access method choices. And so then once we have all these possible plans, we need to actually generate a cost estimate for each of them. And it's common that database systems use a dynamic programming technique, which you may have heard about in your algorithms class, in order to reduce the total number of cost computations that we have to do. So I just wanted to show an example of kind of what this sort of final cost estimation step would look like. So let's say we're just considering the different join ordering. So we start out with RST. None of them are joined, and we say, all right, maybe we would join R and S first, and then T is yet to come, and then maybe alternatively T and S, and there are many other possible join orderings below. And so what we would say is for each of these possible orderings, we're just this kind of first step of the plan. So this is like what should this first node be? Then we'll say, all right, well, we could do a hash join, and that would, I don't know, cost 300. Or we could do a sort merge join, and that would cost 400. If we, with this plan, we could do a hash join, and it would cost 200, and we could do a sort merge join, and it would cost 280. And so for each of these possible first steps, we've computed different plans. And what we'll do now is just choose the best one for each of these first steps. So we're not we're not kind of computing the full path from here to our goal of all three joined together. But just this first step, I'm going to say, all right, the hash join for this one is better, the hash join for that one is better. And then now that we have kind of this first step, we're going to, again, look at each of our possibilities where we say, well, we could use a hash join to join T with this output, and its cost is 380. What about a sort merge? Pretty slow, costs 400. This one, sort merge, costs 300. And here our hash join is actually not so good. It's 450. And so then, all right, this between these two, hash join is better. Between these two, sort merge join is better. And so now that we've kind of done the estimates for each stage, we can say, all right, which of these full paths has the lowest cost? 500 versus 680. So this is kind of the estimate of our kind of best possible possible cost. And so the way that this saved us from some computations is that we weren't considering both combinations here with both combinations here with both combinations further down the line. We're just kind of taking one stage at a time, and this is the way that systems can reduce the amount of cost estimations they need to do. One neat aside is that Postgres has a kind of a way that it kind of does these estimates for queries that have 12 or fewer joins. But if you have a query with more than 12 joins in Postgres, it actually has a genetic algorithm that it uses to try and evolve the optimal query plan by generating a population of possible query plans and doing a cost estimate for all of them, throwing away the worst ones, and then producing a new generation by kind of mixing and matching between the existing plans. You may be saying, well, more than 12 joins sounds like more than any reasonable query would ever have. And well, in practice, actually, if you say Walmart had a database which you want to say, all right, show me the top the top 10 most best-selling items in July in the southwest of the United States, items that weren't on sale, that weren't produce, and as you kind of keep building out this query to answer some specific, say, business question, you could definitely quickly end up with more than 12 joins. And so I thought it was interesting that Postgres has this kind of different optimization technique that it switches to when there are so many joins that this sort of raw enumerate all the possibilities stops being such a good idea. So one key idea that has led us to everything that I've talked about so far today is the fact that SQL is a declarative language, meaning that when someone writes a SQL query, they're just describing the attributes, the shape, the types of result that the query should produce. And the query says nothing about how the system actually needs to execute it. And so I've mentioned this before. It may have seemed like sort of an abstract concept. What does it mean that the system gets to choose? And now that we've dug into kind of all the different ways that the query planner and optimizer may take the SQL input and drastically kind of move operators around, try a bunch of different possible plans. This is the power of a declarative language. By giving up that control, by the user not specifying, use this for loop and then this if statement and so on, the way that you would if you, say, wrote Python code to compute the same output as the query. By doing it in this declarative way, we hand this control over to the system, and in fact, we can make software that is quite good at coming up with these potential query plans. Less good at accurately estimating them. Query optimization is in no way a solved problem. Lots of active research on different techniques, but nonetheless, it has taken us a long way, and it comes down to the fact that because SQL has this declarative aspect, it empowers database systems to do this sort of optimization. All right, with that, I'll bring the video to a close, and I look forward to your questions. Oh, this is different. I think I'm optimizing, becoming one with the multiverse.
It's a trap!